Okay, so we're looking at the graph of that last function that we found the concavity for, if you can remember some of those numbers. Anyway, this nice feature here that Google now offers, I just typed this into the Google search box. Actually, I'm using Google Chrome, and I guess I need to mention this. And I'm actually typing this in up at the address bar where it says, where you type in google.com. Anyway, I'm typing this in and this comes up. Sometimes when I type this into the Google search engine, I don't get this graph to come up, so I don't know what the reasoning behind all that is. But anyway, so we can look at the graph here, and hopefully you remembered some of those numbers. As you can see here, the graph has a local minimum around in this area right here, and then we got a maximum here, relative max, and I should say relative, and then relative min here. Um, I guess depending on the interval that we're on, if we're on the interval from negative infinity to positive infinity, these are considered really global mins here, and this would be considered to be a local maximum. You could say relative maximum, right in here. So anyway, where are we at here? Oh, we're talking about concavity. And the point of inflection, so remember that's where the concavity changes. So as you can see, remember I say concave up, it holds water. And then concave down, right, it doesn't hold water. Concave up, it holds water. Okay, so somewhere in here's a magic point, and that point we call the inflection point, where the concavity changes from being concave up to concave down. Okay, and we found that inflection point, and that was at the it was 2, let's see, negative 2 over the square root of 3 and negative 20 over 9, which was the y value. So that's somewhere about right in here. Okay, somewhere in this area right here is going to be the concavity, or the inflection points, I mean. Okay, so I'm just kind of guessing it here, from about right here and then up, right, it's concave up, and then you can see concave down, right, and then concave up right here. Okay, well that's enough about this problem. Let's move on and work some more. Alright, well, we're just going to go straight to the graph on this next problem here. This is the function here that we're going to be working with. This is x times x plus 3 raised to the half, which is, I'm going to have it written out initially as the square root of x plus 3. Anyway, so this is the graph down here. Nice, interesting graph. And if you notice, the graph stops right here, and there is no more graph. And that is because the domain of this function up here, you plug anything less than negative 3 into this thing, you get a negative under the square root. And of course, then we get into the imaginary stuff. But anyway, so the domain of this function is everything greater than or equal to negative 3. Okay? So that means we're looking at the graph from negative 3 onward in this direction. And you can clearly see by this graph that it's concave up, right? And it's going to be concave up from negative 3 to infinity. And we're probably not going to find any inflection points because the concavity of the graph is not changing. We can zoom out some more on this graph and take a look at it, and as you can see here. Okay, so let's get to the whiteboard and figure this out. Okay, so I'm going to say that there's going to be a lot of algebra to deal with in this problem. I'm not going to get caught up in a lot of the algebra. This is not supposed to be an algebra class, but it's supposed to be a calculus class and learning some techniques in calculus. Now, we're initially given this right here. And of course, we need to go ahead and get this out of radical form and write it in exponential form.